All right, now, there's two possibilities here. If D happens to be the greatest common divisor, since it's a divisor of A and B, it could be the greatest common divisor. If it happens to be the greatest common divisor, then it equals X, okay? But if D isn't the greatest common divisor, that means that, yeah, let's just say else. We'll use some little coding language here. Else, if D is not equal to the greatest common divisor, well, by virtue of it being, the GCD being the greatest common divisor, that implies that D is less than the greatest common divisor of A and B, which is equal to X. So we have here that D is less than X. So either D is equal to X or D is less than X. Okay, now, all right, let me make sure I get this right. Okay, okay, we can combine those. Let's, hold on, sorry. Let's combine those into one statement, combining with D is less than or equal to X. Okay, great. Let me just think for a second. Okay, so we have D is less than or equal to X. Okay, we also know that X, we know that X divides, we already established that X divides A minus B, and we know that D divides A minus B. Okay, but D is any divisor. So both X and D are common divisors of A minus B, and whoops, we are out of paper. There we go. Okay. Both X and D are common divisors of A minus B and B. All right, but X is bigger than B, is either bigger than or equal to D, which means, and D can be any divisor, that means that, that X is, this implies that X is equal to the greatest common divisor of A minus B and B. Okay, so, yeah. And this is, I wrote this like this, assuming that A minus B is still greater than B. But, you know, or it doesn't really matter, we can switch them other way around. But the point here is that we just showed that if X is the greatest common divisor of the first two numbers, when I subtract the one from the other, the greatest common divisor of those two new numbers is the same. Okay? The advantage here is that A minus B is a smaller number. So we just made the numbers smaller. All right, and we keep going until we keep repeating until A minus B is equal to B. And then once A minus B is equal to B, we're back up here in case 1 with A equal B. All right, so that is the justification for the Euclidean algorithm. The last thing we want to know is, how do we know that eventually we're going to get A minus B is equal to B? I mean, it's possible, you might think that it's possible to go on infinitely and just never get A minus B is equal to B. Unfortunately, or fortunately, actually, it is not possible to go on forever. It will terminate. And how do we know it will terminate? Well, we know that it will terminate because of this back here. Because it's actually division. What we're actually doing is dividing and finding the remainder. So, you know, when you learn to multiply, multiplication is actually repeated addition. Well, division is actually, in some sense, repeated subtraction. So the subtractions that we're doing over and over again is just division. And when you divide, the remainder that you get here, right, is always less than the number, the quotient you started with here. If it's not, you didn't do the division correctly. Okay, so with each step, our quotient gets smaller. because this number here is bigger than this number here, and then this number goes here, and then we get a smaller number here for the remainder. So the remainders keep getting smaller and smaller. But since we initially started with the fact that A is greater than B, we're eventually going to run out of numbers. We're either going to have the remainder, the remainder is going to get smaller and smaller. We get less options. For example, when our quotient is 102, the remainder can be 0, 1, 2, 3, dot, 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 all the way up to 101. So I have 102 choices for the remainder. Well, when I do 51, I only have 51 choices for the remainder. If I kept going, I would keep getting less and less choices for the remainder until eventually I'd get down to only one choice for the remainder, and that choice would be 0. And once I get down to that far, it has to terminate. Now, a lot of times it terminates before that, but worst case scenario is that the two numbers are relatively prime, in which case the greatest common divisor is 1. And it actually might be instructive, so let's do it. Let's pick two relatively prime numbers. Let's pick two prime numbers that aren't prime themselves, but that are prime. So let's do like the GCD of, say, 15. No, let's do 21 and 16. Okay, so 21 and 16. So we do 21 and the GCD of that is equal to the GCD of 21 minus 16, comma 16. 21 minus 16 is 5, so that's the GCD of 5 and 16. We switch those around, GCD of 16 and 5, because we can do that. And that is equal to, we again subtract the difference, GCD of 16 minus 5, comma 5. And that is equal to the GCD of 16 minus 5 is 11 and 5. Okay, great. So we subtract them again. GCD of 11 minus 5, comma 5 is the GCD of 6, comma 5. Great. We get the GCD of 6 minus 5, comma 5 is the GCD of 1, comma 5. We switch it around. GCD of 1, 5, comma 1 is equal to GCD. Now I'm going to start doing this in my head because hopefully at this point you should recognize that when you have GCD of anything, comma 1, the answer is 1. But let's just do it out. So 5 minus 1 is 4, comma 1. Now do it again. GCD 4 minus 1 is 3, comma 1. 3 minus 1 is 2, comma 1. And GCD of 2 and 1 is 2 minus 1 is 1 and 1, and that finally is our definite termination point. GCD equals 1. Okay, so you see that even when the two numbers are relatively prime, it's going to terminate. And obviously you get 1 as your GCD, but it works. Okay, so this is the Euclidean algorithm. So let's write out the steps here. Well, briefly here, the steps are you either Euclidean algorithm. Okay, so 1, we'll do the, let's do the division version, okay? Let's divide larger by smaller, and then we take the smaller, divide the larger by the smaller. Well, I'm sorry, step 0. Let's start with that. Step 0, check to see if numbers are equal. If yes, GCD equals numbers, else continue. All right, so then we divide the larger by the smaller, and then we, if remainder equals 0, then smaller is GCD. Else continue. Then we divide the smaller by the remainder, all right, and go to step 2. All right. That is it. It's actually pretty simple. So kind of cool, because finding GCD is sort of, you might think it's sort of a human thing, that you have to be thoughtful about it. You have to try them. You have to look through the list to find them. But actually, it turns out to be incredibly algorithmic. All you need to do is do some processes, do some steps, repeat them over and over again, and you are finished. All right, so that is the Euclidean algorithm.